Okay, so in the last lecture, we discussed two different cost functions. If you remember, the first cost function was, using a step function, which we saw that it had a problem because it had multiple there were breaks and it was highly discontinuous, as you can see from this particular figure also. And then we realized that can we do something better other than that of the step function. So then we saw, like, we can come up with this logistic sigmoid function which actually mimics the behavior of unit step function. And as you can see, if you increase the value of this parameter theta over here, just a second, theta over here, then you can observe that how this approximation becomes close to the unit step which is shown over here. So we saw this also, and then we use that this particular approximation as the cost function in our analysis. And what we observed is, this function, though it is it's differentiable, but the problem is it is also some sort of convex, it is also non-convex. So it has multiple local minimas, and there is a high chance that your optimizer, if you initialize that optimizer at a certain point, it will get stuck into some of the local minimas of this particular non-convex function. That is the main problem with this particular function. So we saw this also already, and we also interpreted the results of the model which is given over here. And what we saw was that any value which is generated by this model, because this is a classification model, so any value that is generated by it is interpreted as the probability of y equal to 1 given the given your data parameterized by theta. So this is basically, we will interpret it as a probability that the class probability of this particular thing belonging to the class 1. So that is again the interpretation of the output of this particular model which we have, which we got. So this is the recap of the last class. So if you have any questions related to any of this, let me know. Otherwise, we will move forward. So any questions? Okay. So if there are no questions, then let us move forward. So in the last class, please remember that I showed you this figure. This figure was not right, and actually the reason for that is, if you see here, the labels, the amplitude was ranging from -1 to 1. So this is not a right figure. As we have this sigmoid, and sigmoid cannot go beyond 0. So this figure was not right actually. So the actual figure is this one, where you can see it is running from 0 to 1. So you are doing some sort of, you are doing you are doing optimization of this loss function, which is given over here, the one which we have here. And then you go you do the gradient descent once you get the optimized value of theta. And then you perform that optimization as we did in linear regression, and this is what it is shown over here. As you can see, how this particular point is getting, moving out, and it settles down somewhere here. So this is just showing you how the optimizer, what is the path of this particular optimizer, how it is moving from an initial point which you have started out with, and how it settles down at this point. So it is showing you on the contour plot of the cost function. This cost function actually is basically the cost function L of theta, which we are discussing in the top. And these are actually not W0. This is theta 0 and theta 1. So this is the cost function, the contour plot of this cost function. This is not G. This is L of theta 0 comma theta 1. So this is the example for this particular case, where we approximated the unit step by sigmoid. So the thing is, now what we observe from this particular cost function, the one which we have defined here. So there is a slight drawback here. The first drawback I have already told you, that it's a non-convex function, And the second drawback that it has is, if you observe this particular cost function closely, it is defined for all values of y. It is defined for all values of y. By saying that means yi can be anything, right? It can go from minus 10 or minus 20 to any range in plus 10 or plus 20. So there is no constraint on on yi. It can be anything. So it's not a drawback, but some way or the other, we are not using a proper cost function which it should take. The classification model, you know that yi is actually either 0 or 1. So there are only two values for yi. But here in this particular cost function, yi is taking any value. It goes from minus 10 to plus 10 or any value. So there is no fixed range. So can we design the cost function in much better way where the cost function should take only yi as 0 and 1. So that is our main concern. And the second concern is, can we make it convex? Right now this is a non-convex function, but can we come up with a cost function which has this constraint also, that yi will be only 0 and 1, it will take only two values, and it's a convex function. So that two requirements actually lead to a better cost function which looks like this. If you observe this here, it's a cost function which is basically divided into two parts. One is when yi is equal to 1. As I told you that our yi in the earlier case was ranging from any value to any value. So we are trying to come up with a cost function which is defined only for two values. So that's why we have these two cases. So one is when yi is 1, another case is when yi is 0. So in case when yi is 1, we define a cost function given by this. If you see here, we define a cost function which is given by this, and it is nothing but this you already know. This is the softmax. This is the softmax thing. Sorry, it's not softmax. This is basically the sigmoid of the hypothesis function which we have already discussed, and then you are applying minus log on this. And when yi is not when yi is 0, then you are taking 1 minus of this and taking minus log of that. So this is basically the cost function for a particular data point I. So here if you observe, I am taking for a particular sample of I, and I is basically running from 1 to m, and m is the total number of data set. So all these conventions are coming from our earlier classes in linear regression. So if you are not comfortable with that, go back and check these conventions. So now this is for all the data sets that you have. So all the points in the data set. So now the important thing is, can we, because this is a conditional statement where yi is equal to 1, you will have this, and when yi is equal to 0, you have something like this. So is there any way that can we combine these two together? So so that it will have one single loss function, and we are good with that. So so that is our main objective. So the thing is, we can do it like this. So what we are doing, we are actually combining this particular conditional statements which is given by here as a single statement, as a single line, a single equation. Sorry. So this will be a single equation here. So now you can see this single equation actually represents both of these conditional statements which are given on the top. So how can you deduce each of them? It is very easy. So let us say, in this particular thing, let us say if your yi is 1, let us say our class is 1. If our class is 1, then the loss function li theta will be minus 1 log of sigma, and then you have this minus, and then when you put 1 here, then it is obviously this particular term will go 0. So there is no such term here, so it will be completely 0. So what is the equation that you are left with? You are left with minus log of sigma x I theta. So this you already know that for this particular case, we are already taking this as the function. So you can see over here, this is already there. And if yi is 0, so what you will do is you will put 0 here. And if you put 0 here, this term will go away and only this term will be left. And this term is actually this term. So now you can see we have combined these two equations, which are conditional equations, in one single equation, which is given by this particular equation. So if you have any questions here, you can ask.
Yes, sir.
Yeah.
So when we had the problem in the first equation when the output was not normalized,
Hmm.
uh, sir, can you go there in that
Uh,
equation?
which one you are saying?
Sir, about
This
this.
one.
Yeah, that one. That
Okay,
one. Right.
okay.
So, sir, here can we normalize the yi also
See
instead
the
of going?
see the thing is, if if you normalize this means what? You will be dividing it by the maximum value. That is what you are saying.
Yes, sir.
So, but the thing is, when you will do that, the problem is that in your classification you have only two labels, right? Either 0 or 1, and
Okay.
you are somewhere or the other trying to convert this data, this yi data, which is of actually regression, to classification. You are trying to do that by normalizing it. So there is no point in doing normalization over here in the case when you are doing a so the thing is, that particular reason which I have given you is just for the explanation, like why we are not using this as a square function, because this particular square function is valid for all yi's. You understand?
Okay.
But we want to define a function which actually takes only two values of yi. It should not, work with other values of yi. That is what our main, objective is. That's why we want to come up with a different function. And the other thing is it's highly non-convex, and we want to make it a convex function. So that is these two,
Yes.
things. The second one is more important. The one which
Sir,
I was telling you.
regarding this, the second one also I had one doubt.
Huh.
So, by non-convex, I understand that there are flat surfaces in the function, right?
Okay, okay,
So,
I will explain you that. Let me explain that also. So, let us say you have a function which looks like this. You understand? So, if you have something like this, then this particular type of function is non-convex. I'm not going into the mathematical details of it, because one of the simple reason for that is, you will get confused. Otherwise, I could have given you a mathematical justification for that. But the important point here is that if you have this type of cost function, what you do is, if you take one point here and if you take one point this side, then if you draw that line over here between the two, then this particular function, which is the blue one, is coming on top of the line which you have sketched here on this. So this should not be the case. In case of convex functions, all the functions should be less than this yellow line which is you are drawing between the 2 points. Right now, as you can see here, this particular part of the graph is actually going above the yellow line. So that's why this particular thing is a non-convex function, as it is going against the definition of convex. But if you have a function which looks like this, then if you draw a line between the 2 points, then you can see every time when you draw a line between the 2 points, the curve is the blue curve is below the yellow line. So this type of property is followed by convex functions. So if you have a function which looks like this, let us say, then will it be convex or non-convex? By
not convex.
Yeah, it will be non-convex, and the reason is, if you take a point here, and if you take a point here, and if you draw the line, then this particular region of the curve is above the yellow line, so it's non-convex. However, it is convex here, but since it's a combination of, since it's a complete curve where this part of the region is not convex, so the complete function will be non-convex. Now you understood what is convex, non-convex thing?
Yes, sir. Understood.
Okay, okay. So now, as you can see now, we have combined these two equations together into one single equation, which is given here. So let us now discuss the physical interpretation of this, like why we have come up with this particular cost function and what is the advantage of that. So if you recall, I just wanted to show you some curves. So if you plot the curve of log of x, so it will, it will be something like this. So everybody agrees with this, I guess. There is no doubt in this. Like if you plot the curve of log x, it will be like this. And this everybody knows. And if you want to take minus log of x, and that curve will be like this. This is minus log of x. So it is a simple thing. You can check it out also on web, or you can draw it yourself also. There is no, you know, intuition behind this. This is just a log x function, and you are, when you take minus log x, it will be like this. So let's focus on this minus log x, because you can see over here we have minus log some quantity. So let us see what it means when you are saying minus log of x if yi is 1. So if we consider the first condition where it is saying minus log of sigma x dot theta if yi is 1. So now we will draw this particular curve here. So as we have already discussed, the minus log x will be like this. But please note, we will not go beyond 1, because as you can see, the curve will extend down also, but we are not considering it. Can anybody tell me why we are not considering it? This is between 0 and 1.
Because according to our function, we take it as 0 or 1 only.
Yes, so the sigmoid that we have, that we are using, its range is between 0 and 1, and what we are saying is even the output of this we are interpreting as, a probability. So the probability normally is between 0 and 1. That's why we are constraining our function, which is minus log of x, in between 0 and 1. We are not going beyond that. So now, if you understood this carefully, now the good part here is to understand what this curve is actually saying, and the curve is actually saying a lot. This is basically your, if you see this, this is basically minus. This is basically loss function. This is basically a loss function. So now, what happens is, if you have a class which is yi equal to 1, let us say, for a particular data point I, you have a corresponding class as 1. So if your output, if the output of your and this is basically, this is this, the x-axis is sigma of x dot theta, and the loss is, as you know, it is log of sigma of x dot theta. So if your actual class is 1, if your actual class is 1, and this is the output of your hypothesis function, the classification output. So if this particular if this particular model gives you an output of 1, let us say, then you are operating at this point or not? Exactly at this point. So what it means is, your model has predicted 1 and the class is also 1. So if the model has predicted 1 and your class is also 1, your model is doing good. Then there is no point in creating the loss function for that. There is no point in penalizing that particular model, because it is predicting good. There is no harm in the results. So what you do is, you do not penalize. You do not penalize the model, and the loss function that you generate for that is exactly 0. But now, let us say if your model predicts a value of zero point 0.6, but your actual data set has a class of 1. So what it says is, your probability of getting a class 1 is 60%. But here the probability of the class is 1, and that probability is 100%. But here it is saying, model is saying it is 60%. So what it means is it is creating an error. It is creating an error because it is giving 60% probability, but that class you already know, because you are learning, you are doing a supervised learning, you already know this class has a value of 1, which is 100% probability. So you are actually operating somewhere here at this point. So if you are making an error, that means you have to be penalized. If somebody is making an error, he has to be penalized. In the same way, in machine learning also, when you are making when machine is making an error, it has to be penalized, and the penalized value will be this value. And now you can see this value is higher than the this value, because here there is no penalization because your model is correctly doing the prediction. But as you go further down towards zero, so as you go further down towards zero, if your model predicts a value of 0, and if your actual value is actual value yi is equal to 1, then you can say your model is completely waste. It is not predicting properly the output symbol. So that means it has to be penalized much heavier compared to the earlier case when it was predicting zero point 0.6. So now you can see the penalization at 0 value is very high. It is very high. So this penalization actually motivated us to use this particular thing over here, this particular cost function. So it's giving you a penalization when yi is equal to 1. So as you also can see, this particular function which is over here is a convex function. So it's already, it doesn't have any local minima type of thing over here. So it's not like, it's not having a behavior which is like this. It's completely, smooth, and there is no local minima here. So that's why we have selected this particular function. So now so any question here regarding the interpretation? So the second function is minus log of 1 minus y of sorry, not this one, 1 minus sigma of x dot I theta. This is our second function, and the case that we are looking here is that our class should be 0. This is our case. So in this case, if you plot the curve of minus log of 1 minus x, because here x is sigma of x dot theta, so that curve will look like this. So again, you will be ranging from 0 to 1. This is your sigma of x dot theta, and this is your loss function. So now if you plot minus log of 1 minus of sigma x dot theta, it will look like this. So this particular curve corresponds to the class when you are assuming that your class label is 0. This is you are assuming, then you are plotting this particular loss function. So now again, if we go by the same logic, if your hypothesis if your hypothesis coming from the classification model, that is sigma x dot theta, if it produces output as 0, then you are good to go, because your output is also 0 and your actual output here is also 0. So the loss function incurred will be 0. There is no loss function, there is no loss. So there is no way of penalizing the machine learning model, it is already doing good. But when your when your machine is predicting output as 1, but it is 0, then you can see the penalization, or you can see how much loss it is creating here. So this is basically the penalty. It's a penalty which is actually imposed on the loss function, because you are trying to minimize the loss, right? You are trying, if you observe carefully, we are trying to do this arg min of theta. This, if you observe carefully, we try to minimize this loss function always, so that we can get the estimated value of theta at. We always do that, as you can see in our regression lectures also. Every time we are doing this arg min theta of L theta. So what it means is we are always seeking for minimization of the loss. We are never seeking arg max of L theta over theta. We are never doing this. We are always minimizing the loss. So when we are always minimizing the loss, so if some at some instant if loss is actually this much high, then we want to minimize it so that we can come from here to here. So if we can move our model from here to here means the prediction will improve. Earlier it is making value of 1 as the prediction which is not good, and then when you minimize the model, when you minimize using the gradient descent, because this you will do through gradient descent or any other optimizer. So what it will do is it will try to adjust the loss function and keep come up with the parameters theta at, so that your prediction improves and it goes back to this from 1 to 0. So that is what actually is happening behind the scenes when you do arg min theta L of theta. So any questions here regarding this?
Sir, just asking this,
Hmm.
that if we swap y from y by 0 to 1, then can we go for at max?
If you swap from y 0 to 1, but basically what you are saying is you want to swap it, or
Uh,
like.
I'm just asking because I just got curious.
Hmm.
We are just swapping. We are making taking the loss function is log of minus 1 minus sigma of xi theta,
Okay.
and we are going for y is equal to 1.
Uh-huh.
So can we uh, can we maximize the loss function now, because we want to go for 1, y is equal to 1.
Okay, so you are saying instead of doing this, instead of using this function for y equal to 1, if we use y equal to 0 here and 1 this side, this is what you are saying?
Right. Yes.
Oh, okay. In this sense, this will create a problem because as you can see here, the log function which is given over here, and if you take it for 0, let us say, so if you take it for 0, then what will be the interpretation? Interpretation is like your yi is 0, the correct one is 0, but you are predicting value as 1, then it is giving you no loss. So it's not giving you any loss at all, but you are making an error here, right? Here it is 1, your machine is predicting 1, but it is giving you 0. So it's a error. Then you have to maximize the loss because you want to penalize it heavily. But right now you are not penalizing it at all, so this will not work. This will not work. Okay. However, these two problems like arg of min and arg of max, they are actually dual of each other. It's just that you apply a minus sign out of, if you put a minus sign out in case of this, it becomes arg max. So they are just dual of each other, complementary of each other. So if you have a problem which is argmax, if you apply minus at the front side of it, it becomes a argmin problem. So these two are dual of each other, but right now we are only considering this particular case where we are doing argmin. Later on, when we will discuss other advanced machine learning algorithms like support vector machine, there you will see what this duality means and how we are doing it. Okay.
Okay, sir.
Okay, so once we are done with this understanding, and if you and then when we and then also you observe that how we are writing it as a combined loss function, which is given over here. So now our next objective is to actually write a combined loss function L. Right now we took it for a single symbol, a single sample L of I, L subscript I. But if you want to do it for the all the data in the data set, then you will be summing it up from I running from 1 to m, where m is the total number of samples in the data set. So then then it's very easy. You just sum it up because earlier we were discussing only for the ith sample, but now we are summing it up from 1 to m, and then you are averaging out by dividing it by 1 by m, and minus is coming because if you observe carefully, both these terms are minus here, so I'm taking that common, so minus will be outside. So you have this combined function which is given over here. So now the next question is how to obtain the optimal value of theta at here. How we can obtain the optimal value of theta at. That is the optimized values, this you have to do it through, optimizer by argmin on this loss function, so that whatever value you will get is the optimized value of theta at, which corresponds to the decision that you are taking, the decision boundary of the classification model. So again, what you will do is once you so this theta hat that you we are asking for to get the optimal value is obtained using gradient descent, as you already know. So in this particular setting, the only term that is unknown is this, which we have to calculate, which is the derivative of the loss with respect to theta I. Uh, this is the term that we want to look for. So let us calculate this term and see how we can derive it. So first of all, before going there, I just want to do some simple calculations, because these calculations will be used in the derivation. So let us say if you have a function which you already know is this is the sigmoid which is applied on the x dot theta. So if you have something like this, because it's already known to you, it's 1 upon 1 plus e to the power minus x. So I'm just putting x dot theta over here. So once you take the derivative with respect to theta and do the analysis, it is very clear and it will be very obvious. Once you do it through this, you will come to know that the sigma hat of x dot theta, sigma hat, this one I am taking as a derivative, the first derivative with respect to theta, that you can write as this in terms of sigma x. You can solve it, it's very easy, there is no magic about it. So what we are doing is we are actually writing sigma dash x dot theta as sigma x into 1 minus of sigma x. This is the thing that you have to keep in mind, that if you have a derivative of sigma hat, it can be replaced by sigma into 1 minus sigma. So this you can check it yourself. So once you have this in your mind, then we can start the derivative process for this particular loss function. So we have this loss function here, as you can see. So once we have this loss function, then what we are doing is we are taking the derivative of the loss with respect to a specific value of theta j. As you know that theta is basically a vector of values theta 0, theta 1, theta 2 till theta n plus 1. So it's a vector, right, which is a value r of n plus 1. So I am taking a specific value of theta to calculate the derivative of the loss with respect to that. So now you can see this is basically a log term. So so log of x is 1 by x. So it will be here. And then we have this term which is log of 1 minus x. So if you take the derivative of log of 1 minus x, it will be this, and then you have a minus sign also here. So because of this is simple derivative rule, so there is nothing fancy about it. So this is log of 1 minus x is, I'm taking 1 minus x down, so it will be here, and then minus sign is there, and then you take the derivative of the loss with respect to theta j of this. So this term, the derivative of this term is actually common to this and this, so I have taken it out. So this is the derivative of the loss, or derivative of the derivative with respect to theta j for this particular expression here. So if you do further analysis on the middle part, on this middle part, you will get something like this. If you solve it, it will be just a adjustment of the terms. So once you have this, then you observe here carefully that we are doing a derivative with respect to theta j of xi theta. So when you do a derivative with respect to theta j of xi theta, you will actually get the xj component of that particular theta j. So if let us say you have theta 0 plus theta 1 x1 plus theta 2 x2, you have this type of thing, right? So once you do a derivative with respect to theta 2, you will only be left with x2, the second feature. So that is what is over here. So once you do the derivative with respect to theta j, where j is the feature which is running from 1 to n. So once you do the derivative with respect to theta j, the jth component, the jth feature of this particular sample will come out, and that is given by this, which is given over here. And then you have a derivative like this, which is the derivative of the sigmoid, which is given like this. So once you have this, then what you can do is everything is same in this expression, but the extra term that is coming out is shown in blue, and the blue term is the extra term that is basically catering to the derivative of the sigma hat. And this we have already calculated here. If you observe, that's why I have calculated sigma hat here, which is actually sigma x into 1 minus of sigma x. So this term we will actually keep it here. So once we keep this term here, what you get is this. And now, as you can observe carefully, that this blue term which is given over here cancels out with the denominator which is given over here. If you observe this carefully, the blue term on the extreme right will cancel out with the denominator term which is given over here. So once it cancels out, you are only left with this particular expression. Everybody agrees with this. So if you have any questions, let me know regarding this adjustment. I think it's simple calculus and there is no thinking required in that. Once you go back, have a coffee and just do these adjustments, you will come to know how this expression is coming. So there is no intuition behind all this. Okay, so once you have this, what you can observe is you can also cross verify yourself the dimensions that I have listed out in the bottom part of it, because these are important, because all these are matrices and vectors. So if the dimensions are not correct, your answer will also not come. So you observe that this particular will have a dimension of 1 cross 1, because you are actually working at a particular value of theta. You are not taking the vector, you are taking a specific value of theta. So it's a scalar quantity, and its value will be its dimension will be 1 cross 1. And when you do the dimensionality analysis on this particular thing, as I have shown you in the blue lines and with the blue markers, you can see the dimension is 1 cross 1. You can cross verify yourself why it is so, but it will come out to be as a 1 cross 1. So this is your derivative of the loss with respect to a specific value of theta j. But if you want to cater for all the derivatives, like we have to look for all the derivatives with respect to theta n, and so the dimension of this will be now Rn plus 1, and there is no subscript on theta now. If you observe here, there is no subscript of theta here, because this theta is actually a complete representation of a vector having a dimension of n plus 1. So that can be done very easily by coming from here to here. What you can do is you can replace them with the matrices. So here now you observe carefully that I am writing it in terms of the matrix form. So here there is no j here. If you see here, there is no j now at this point. So there is no j, and even here also there is no j. As you can see here, there is no j at this point. That's why uh, we have something like this. So you can check for the dimensions. So once you check for the dimensions, you will get the derivative of the loss with respect to theta j for theta for every value of for every value. Right now, in earlier case, it was 1 cross 1 only, because you were looking for a specific feature in the ith sample. But now you are looking for all the features. So obviously, dimension will increase to n plus 1. So this is basically the derivative of the loss with respect to theta and not with respect to theta j. So you can now write the gradient descent as this. This is the equation we already discussed, and then this part, the derivative of the loss with respect to theta j, can be written as this, which we have already derived now. This thing. So here you can note that we are doing we are doing gradient descent on each value of theta j. So you are running your loop from j running from 1 to n, and then running your loop from 1 to n, and you are doing individually all the thetas individually. As you can see, the equation is also saying that. So let us try to avoid this for loop, which is like, as you will run the loop from j1 running from 1 to n, we should avoid it because it slows down the process if your n is large. Because for every step of j, you are actually running this sigma from 1 to m. As you can see, there is a sigma which is running from 1 to m. So if your m is, let us say, 10 to the power 6, which is quite common because you have large number of samples in the data set. So for every value of theta j, you are actually doing this summation, so that actually slows down your algorithm. This is also one of the important things to keep in mind, that your algorithm should not slow down as you do these type of things. So we have to come up with faster way of implementing it, so that it is very easy to, so that the updates of the theta j can be make made faster. So how we can do that? We can do that if we can vectorize this theta. As you can see here, this is the element of theta which is represented by theta j, but now it is a vector form here. So if we can make a vectorized implementation of that, and if we can get rid of this particular thing, if we can get rid of this particular thing, then also we are good to go. So what we have done is, this equation at the top is the same as this equation, because as you can see here, I have represented in this form here. But right now you observe that in the first equation we had theta j, but in the second equation it's a vector, because I have taken all the elements of xi and not j, because here there is no j, so I am taking all the consideration of the feature vectors. So it is now x of I, this thing. So this is again the same equation as this one, but written in more better way as compared to the earlier case. But now there is a problem. As you can see, one problem we have removed. The first problem was that this jth component, which was actually, you have to do it till n times, at least it is solved by taking x of I, which actually caters for all values of j running from 1 to n. So that type of loop which is coming from here is solved by using this particular vector which is given over here. But now the second problem which is coming is because of this summation sign, which again slows down the things. The first was due to this, and the second one is due to the summation sign. So let's see how we can remove this summation sign. So it is also very easy. You can remove it by coming up with the vectorized implementation. As we discussed last time, we will, we will see it in our next class, how to remove this sigma, which is the vectorized implementation of this summation. We want to remove this summation sign. So we will see in our next class, because I have some things to, do. Uh, so the thing is, we will see how we can remove this sigma, which is the main slowing factor here. So any questions here in understanding this? Any questions from you people regarding whatever we have discussed today? So this is also called as binary cross entropy, the loss function which is given over here. So this is called as a binary cross entropy loss function, and you can look for it in details. And regarding the vectorized implementation, you can try it yourself also, and we will discuss in the next class that how we will do that when we try to replace all these equations by the corresponding matrices and see how fast we can go about that. So any questions here regarding this? Any one of you? Okay, so if there is no questions for today's discussion, so let's close this class today, and then we will meet next time. Thank you.
Thank you.
Thank you, sir.
Thank you.